Hey y'all, it's Mr. Boyden. I'm back at it again. Today we're going to be writing algebraic proofs. Now you probably were exposed to proofs back in geometry is my guess, and well, you probably had one opinion or another about them. These ones I think you'll find to be a little bit more elegant and hopefully a little bit more beautiful. Certainly I do. I enjoy these ones a lot more personally, so hopefully you do too. Let's start out with a simple claim that I think anybody could understand. This claim is, and I heard this one in a newspaper article a few weekends back, that there's only one solution to the Pythagorean theorem that is composed of three consecutive integers. And so what they're talking about, we know the Pythagorean theorem, a squared plus b squared equals c squared. What they're claiming is 3, 4, and 5 are solutions to this equation. So 3 squared plus 4 squared equals 5 squared, and you can verify that if you want to. But that's three numbers in a row, three consecutive integers. What they're saying is there is no other place where you're going to have three consecutive integers that come together and make a right triangle. This is the only one. Now, we can think about this broadly. We could do it visually, and it's actually pretty easy to understand because just think about what happens as these numbers get very large. Like, let's say you had numbers like 99, 100, and 101. Three consecutive integers. Well, think for just a minute. If you drew out a triangle with these side lengths, what would it look like? And yeah, it is a scalene triangle because all three sides are different, but scalene triangles can be right. We have an example right here of a scalene triangle that's right. But specifically, what would this look like? All of these sides are within 1% difference of each other, which means they all visually would look like they're about the same. This triangle would look like it's equilateral. Now, it wouldn't actually be equilateral, but the larger that these numbers get, in terms of their percentage differences, they're actually getting closer together. So we can kind of just think through the fact that, okay, well, for small numbers, maybe there's a solution. We can kind of justify that for large numbers, there's not going to be another solution that consists of consecutive integers, but that's not a proof. That doesn't really prove anything. So let's set out to write a proof. Let's do it like this. Let's write out three consecutive integers. A is an integer. What would be the next biggest integer? How about a plus 1? And after that, how about a plus 2? Let's run them through the Pythagorean theorem. Squared, so each of these is going to be squared. A squared plus b squared equals c squared. And so what we've done here is we've just basically set up a mathematical equation that represents the claim. They said you're only going to get one solution out of this. Let's play around with it and see what happens. So a squared is just a squared. Let's see what happens here. Now remember, y'all, some of you might be tempted to distribute that square, but we got to FOIL it out. So if you need to show that on the side, pause the video and do that. You get a squared plus 2a plus 1 equals, and over here you got a FOIL as well, so you get a squared plus 4a plus 4. And what can we do with that? Let's simplify some stuff out. So you could subtract a squared on both sides, and we could do minus 2a on both sides, and we could do minus 1 on both sides, and let's see what we have. I get a squared equals, boy, all that went away, that's nice, and then 2a plus 3. Cool, so we're down to a simple quadratic. Let's rearrange all the terms on the left side. So we get a squared minus 2a minus 3 equals 0. And let's see if that's factorable. That factors into a, 3 and 1, and it looks like it's minus 3 and plus 1. So what does that mean? It means that a is equal to 3 or that a is equal to negative 1. So let's consider what that means. We said there would only be one solution, a unique solution. And this says there's two solutions, one that starts with 3, which by the way, if it starts with 3, it's implying a 3, 4, 5 triangle because we had smallest, next biggest, next largest in our setup. That's here. In this one, what Pythagorean triple does that allude to? Negative 1, 0, and 1. Well, what kind of triangle has side lengths of negative 1, 0, and 1? That's not really a triangle at all, so that's an extraneous solution. So what we found, we had a setup that matched the claim, we worked it out, and we found there was only that one unique solution. So that proves that this is true. So that's really what we're going to be trying to do today, is we're going to be trying to find logically, not by testing lots of numbers, because you'd be testing forever, there's infinitely many numbers, something elegant like this that leads down to some sort of a simple result. So let's continue with it. Now, there is something in our curriculum that's called a left-hand side, right-hand side proof. So LHS, RHS. left-hand side, right-hand side. The way this works is exactly like our previous learning with verifying trig identities. And they tie together really nicely. So all it means is you can only work on one side at a time. You can't move things to the right side, you can't subtract 5, you can't multiply by 6, things like that. But what we could do in a case like this is we could add the fractions by getting a common denominator. So multiplying by 3, numerator and denominator, and I would get 1 plus 3 over 12, which would be equal to 4 over 12, and 4 over 12 would be 1/3. So, and I'm going to be just a little bit quick here, so that's 1/3 equals 1/3. Okay, that's a really simple example. It's not really a proof, it's just kind of a reminder of this style of thinking. Okay, so that's what we're doing, but now we're going to try it with an algebraic example. Okay, and so here is our first one. All right, very similar to the one we just saw. It might look a little bit harder, but it's not really harder. Okay, we'll have to be a little bit more creative though. So again, we have fractions that are being added together. One thing that stands out to me right away is that this chunk of math right here, both of those terms have an m in common. And so what I want to do, I want to factor out the m so I can see if there's something to that or not. So m times m plus 1. This right here, that triple bar, it means equivalent, and that's a hint that, hey, you can't do stuff on both sides of the equation. You can't add or subtract on both sides, things like that. So this is still 1 over m, and then over here we have 1 over m plus 1. Now, why that factoring is helpful, when we go to get a common denominator, we ask the question, what do they have in common, and what does one not have that the other one does have? Well, in common, they both have m plus 1. This one on the left does not have an m. Now it does. Okay, and as long as you do that on top and bottom, so you're really multiplying by 1, it's all good. Okay, so here we go. What do we get? M times 1 is m plus 1 over m multiplied by m plus 1, equivalent to 1 over m. And then look at that. We have m plus 1 on top and bottom, so those are going to cancel out. And we get 1 over m is equivalent to 1 over m. So we took something that didn't look like it would necessarily be true, you know, two really nasty fractions added together to equal this simple fraction, and yet it is true. Okay, so that's a demonstration by left-hand side, right-hand side, that those two things were the same. All right. Now the next type of proof we're going to write about, and these ones are even a little bit more simple, we need to know how to write odd and even numbers. Now, if you remember back to one of the very first videos in pre-calc, and if you took my class one of the very first days of the school year, we talk about sequences and series, and I'd put a list on the board like 2, 4, 6, 8, and we'd try to write a rule that described that sequence. And a lot of people write n plus 2. But as we saw, if you write n plus 2 and you plug in a 1, 2, 3, you get 3, 4, 5. That pattern is not addition by 2, it's addition by 1. So in fact, what we need is 2n, and you could probably do mental math on this. 2 times 1 is 2, and 2 times 2 is 4, and 2 times 3 is 6. And so this is what an even number looks like. Odd numbers. Odd numbers like 1, 3, 5, 7, what we did in the beginning of the year, at the beginning of the videos, is we would say, well, what's different about these numbers? The pattern is the same, so there's still going to be a 2n, but each of these numbers, like 1, is 1 smaller than 2, and 3 is 1 smaller than 4. So this needs to be 1 smaller compared to the evens. Okay, so this is on the left, 2n is how we represent even numbers, and on the right, 2n minus 1 is how we represent odd numbers. So with that, let's go and write some proofs around even and odd numbers. Here's our first one. We want to show that the sum of any two odd numbers is even. Okay, so what we're going to do, that's a sum. We're just going to translate this down into algebra, kind of like maybe we even did something like that in Algebra 1, turning a situation into an equation. So any two odd numbers, let's write our first odd number, 2n minus 1. The mistake that a lot of people make is they write 2n minus 1 again. But that's not any two odd numbers, that's the same odd number twice. And so the way we get around that is we can just change this variable, like let's make that m. So now we have 2n minus 1, 2m minus 1, and we need to try to show that that's even. Okay, let's simplify down a little bit. So what can I do? I can write 2n plus 2m minus 2. So how do we know if that's even? Well, let's remember what an even number is. An even number is one that is divisible by 2. Or another way of putting that is that 2 is a factor of the number. So what that means is if we could factor out the number 2, it would be even. If we could not factor out the number 2, then it's not even. Let's try it. So these all have a 2 in common, so n plus m minus 2. So to finish our proof, we should probably write something about it. So we could say, since 2 is a factor of the quantity, it is even. And that proof is done. We've shown our work. I've written a concluding statement here so that a reader could follow the work and try to understand it. And so that suffices. It is proven. Let's do another one. This one's fill in the blank style because I think you could probably fill in the blank. If you felt like the last example made sense, why don't you pause the video and try this one on your own? Show that the sum of any two even numbers is even numbers like 6 plus 8 equals 14. That one's even. Like 2 plus 4 is 6. That's even. Seems like the answer to this might be even. Let's show it. 2n is an even number. It said any two, so I need a different even number. How about 2m? And we could factor out a 2. And I'm going to be a little bit cheeky here. I'm going to go actually grab that text from the last one. And so it's going to be the exact same thing. Since 2 was a factor of the quantity, then it is even. Okay, and that's the end of a proof. So these don't need to be super intimidating. If we know what even and odd numbers look like, they're actually kind of fun. All right, let's look at a test type of question. And here it is. And this is another chance. If you want to pause the video and try it on your own, that would be awesome. All right, so part A, show that this big old equation is true. And where n is an element of the integers. All that's saying is that n has to be integers. It's actually a good thing. It means no decimals, no weird fractions, nothing like that. And then, hence or otherwise, prove that the sum of squares of any two consecutive odd integers is even. Let's do part A first. We'll come back to that. Okay, so I'm going to zoom in so I can write a little better and see a little better. What I'm going to do for A is the exact same thing we've been doing in all the other examples in this lesson. I'm going to just try to simplify this out, and I'm going to see where the math goes. So if you want to write on the side that I'm kind of foiling this out, like 2n minus 1, 2n minus 1, if you get confused on this step, it might be because you forgot that that's what I'm doing here. So with that, I'm going to proceed. So we get 4n squared minus 4n plus 1. And then we're going to do this one. So I'll put a plus so you can see a break in the two terms, or the two chunks, I guess, that came from the different binomials. So that would become 4n, and then plus 4n, plus 1. And supposedly that equals 8n squared plus 2. And let's see, 4n squared plus, I forgot the squared. 4n squared plus 4n squared is 4n squared. Negative 4n and 4n cancel. And 1 plus 1 is 2. Now, do you see the mistake that I've made? I bet that some of you are just absolutely screaming at the screen or giving me funny looks right now because I absolutely have made a mistake. So where is it? Right here. Don't know why I did that. So 4n squared plus 4n squared is 8n squared, and that's a good thing because now the two sides are the same, so part A is done. Now, for the second part. Hence or otherwise, prove that the sum of squares of any two consecutive odd integers is even. All right. So when they say hence or otherwise, usually it's easier to do the hence if you see it because they're saying, hey, just so you know, you already did most of the work for this, so just go ahead and finish it out. So first of all, we need to talk about how the hence would work. So they said prove that the sum of squares of two consecutive odd integers. So we're going to say, first of all, in part A, and then 2n minus 1, oops, I did x, so 2n minus 1 is an odd integer. And 2n plus 1 is 2 larger and also odd, so it is, so these are, I'll say, so these are consecutive odd integers. I demonstrated that their sum was 8n squared plus 2, which can be factored into, and so we just pull a 2 out of that, so that'd be 2 times 4n squared plus 1. And then I will say, since it has 2 as a factor, it is even, and hence the sum of the squares of any two consecutive odd integers is even. Okay, and that completes it. So just a little explanation on that. When we did most of the work, I did one factoring step, and that was enough to show that it was even. I also had to say that I understand that part A, that written out algebraic statement, matches the part B. But that's it. So now that's done. That's how it goes. So this is a proof that I really enjoy. It is thousands of years old. I think it's attributed to Euclid, actually, from way back in Alexandria. And so here it is. It's how many prime numbers exist. Now, when I did this in class a couple weeks ago, most of the students were quick to say infinitely many. And when I asked them why, they said, because my teachers told me so. And I mean, I guess that's fine, but it's not very satisfying anyway. So prime numbers, we know numbers like 3 and 5 and 7, not 9, 11, 13, not 15, 17, 19, not 21, 23, not 25, 27, nope, 30, nope, don't think so, 29 maybe. Okay, so one thing that you might be able to see already is these numbers seem to be getting more and more spaced out. So the question is, do they ever get so spaced out that you could not see the next one, or that the next one wouldn't exist? We're going to prove this with something called a proof by contradiction. And so here's what we would think about. In terms of what's true about prime numbers, either there exists a finite number of primes or an infinite number of primes. One of those two things has to be true. Okay, so what we'll do is let's play around in the world that has finitely many primes, and let's see what happens. If it's true that there are finitely many primes, then there must be a biggest prime in that world. Okay, let's kind of separate these out a little bit. Because if there's finitely many, they couldn't all be the same size. There must be one that's bigger than the others. Well, let's consider what that would look like. I could make a number like the first prime multiplied by the second prime multiplied by the third prime, and so on, all the way up to the biggest prime. We could multiply all of the prime numbers together. Now, would that number be a prime number? No. In fact, it's divisible by literally every prime number. So that's not a prime number. Okay, well, let's add 1 to that number. So now we ask again, is this number prime or is it composite? Composite is the opposite of prime. It's composed of multiple factors. So prime or composite. Well, let's see. It would be composite if it were divisible by any prime number. So is this divisible by any prime numbers? Well, if you divided it by p sub 2, you would have a remainder of 1. If you divide it by p sub 3, you'd have a remainder of 1. If you divided it by p sub n, you'd have a remainder of 1. So this number right here, it's divisible only by itself and 1. Well, wait a minute. That's the definition of a prime number. So we just demonstrated that in a world where there are finitely many primes, there must be a biggest prime, but that's nonsense because I can make a bigger one. So if you say there's a biggest prime, I can make a bigger one by multiplying them all together and adding 1, and that will be guaranteed to be a prime number. So how does that make this a proof? Well, we just found that if we assume there's a finite number of primes, we run into a contradiction where we can find a bigger one. And if you can always find a bigger prime, then the only logical conclusion is that infinitely many primes must exist. And that turns out to be the truth. Okay, so that actually is a full functional proof. This is what we call a very elegant proof. It doesn't have lots of steps. It doesn't have lots of moving parts. It's just a logical proof. In fact, I mean, I guess technically I wrote a little bit of algebra down here, technically, but it's not even really an algebraic proof. It's just very elegant and beautiful. The last thing we're going to look at today is a proof of Thales' theorem. Thales is another ancient Greek who came up with a theorem, and I really like the proof on this one. I find it to be very pleasing. So let's take a look at it. So, what Thales' theorem is we start with a circle, and on that circle we construct a diameter. It does not matter which diameter it is. Some people say, well, you made it horizontal. It doesn't need to be. It could be anywhere. In fact, let's make it not horizontal just to make sure that's really clear. And then if we pick another point on the circle, and I'm going to put a point for that diameter, and we connect the points, it makes a triangle. So end points of the diameter and a third point. That third point, it doesn't matter where it is. What Thales' theorem says is that no matter where you put this point, that angle right there is a right angle. So, let's try to prove that. One of the cool things about proofs is that for a lot of different theorems or ideas, there's more than one way to do it. Like the Pythagorean theorem is famous for having hundreds of different proofs. This is my favorite proof of Thales' theorem. Okay, remember we're trying to show that this angle right here is a right angle. Okay, so that's what we're going to be after right here. Now, first thing I want to notice is this segment from here to here. In fact, just so I can talk about them, we'll call it A, B, C, and D. From A to B, that's a radius, and B to C is a radius. So I'm going to mark those as being congruent, because they are. And I'm going to draw in from this point to the center. Now, how does the length of that segment compare to the length of those two we just named? This one is also a radius, so it's the same length. Now let's consider one triangle at a time. Let's look at the one on the left first. What kind of triangle is it? Two sides are the same. One side might be the same, might be different, but it looks like it's an isosceles triangle. It's probably not equilateral. So let's go like this. That means that whatever angle this is, I'm going to call this alpha. This angle is the same thing. Okay? What about this triangle on the right? It's clearly not the same triangle, or at least it looks different. It looks like it's an obtuse triangle. However, two sides are the same length, so this is also an isosceles triangle. We'll call each angle beta. Why alpha, beta, not A and B? Because Thales was Greek and feels like a nice tribute. All right, so let's look at what we have here. We have this angle of the triangle marked as beta. We have this angle marked as alpha, and we have this third angle. It's two angles now, but we've got that marked as well. But we can remember from geometry that the sum of any three angles of a Euclidean triangle is 180. And we proved it back in geometry class, and so we can rely on it now. So what are the three angles? The first angle is alpha. What's the next angle? The next angle is alpha plus beta. And what's the third angle? Third angle is beta. Well, that looks like we could simplify it. How about 2 alpha plus 2 beta equals 180? And it may jump out at you that both sides of this equation are divisible by 2. So that would then say alpha plus beta equals 90. Well, that proves it. That says that no matter what these were, no matter where you drag this point, because it's still going to be an isosceles triangle, and an isosceles triangle on the right as well, that this angle alpha plus beta is going to equal 90 degrees. So that's a complete proof. It's done. That proves Thales' theorem is true. So, what could you practice to get better at these? Okay, there's some suggested exercises which I'm going to leave here on the screen for a minute here at the end of the video. This would be a really good thing to practice right now to build up some skills on those odd and even problems. As far as for my class, if you're in my class, I usually don't test on things like Thales' theorem or the proof of primes. I include them because for a lot of people, these questions are so basic that they're not really inspiring or exciting, and for some people it can be pretty exciting. I know it was for me the first time I saw Thales' theorem. You go, wow, that's really elegant, that's really, really cool and kind of surprising. Same thing with the primes, the logic, I just found it to be really cool, so I wanted to share that with you as well. But this stuff down here is more similar to what you would expect to see on a test, and the same at the very beginning of the video as well. Those are more like what you'd expect to see on a test. So hopefully you enjoyed the video, hopefully it was helpful, and I'll see you next time.